Hello, everyone. In this video, I'm going to talk about longest common subsequence. Suppose we are given two sequences. Uh, One of them is X, the other one is Y, and we want to find a longest common subsequence of X and Y. So in order to talk about this, so let's look at what a subsequence is. Okay, so now let X from 1 to M be a sequence of symbols. X1, X2, up to Xm. We can think of each of these Xi's is a character. So think of X as a string. Okay, then we just pick. So for instance, let's say we have X1, X2, X3, X5, X6, X7. So we just pick some of them to form a new sequence. For instance, if we pick X2 and X5, we get X2 and X5. So this is a subsequence of X. So this is subsequence. Okay. And so in general, if we simply select some indexes, let's say I1, I2 up to X, up to IK, such that I1 is greater than or equal to 1 and strictly less than I2, strictly less than blah, 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 strictly less than IK, and less than or equal to M, then this new sequence is a subsequence of X. So with this understanding, then for two sequences, X and Y, a common subsequence will appear in both X and Y, and among all of these common subsequences, we would like to find a longest common subsequence. Okay, and remember that we may have multiple longest common subsequences. They have the same length, but the sequences are different. So that means that we just need to find one in this case. All right, so how do we find a longest common subsequence of X and Y? And obviously, we could try the naive approach by looking at all possible subsequences and then check whether they are common subsequences of those of X and Y, and then pick the one that has the longest, has the largest number of symbols in it. So that obviously is not efficient. So now let's find out what would be a efficient method, and we are going to use dynamic programming. So we're going to use DP. So in order to do so, we first need to formulate a problem, and which means that we want to have a name. We want to give a name, and then we also want to give a parameter or more parameters. So in this case, we could use LCS to indicate longest common subsequence. So we want to find out the value of the longest common subsequence. And then we are given two inputs X and Y. So we could think about that X capital I is from X1 to I, and Yj is the prefix of Y. So this is a Y from 1 to J. Okay, so this is a prefix. And what we are trying to do now is we want to find LCS Xi Yj. And so which means that we look at its prefix. Okay, so we want to find out the longest common subsequence of both prefixes. And then the original problem then becomes LCS X, Y. Okay, so for simplicity, let me just remove the X and Y, so we use I and J. Okay, so that's what we do. So let the LCS be the name of the problem, and I and J be the two parameters, and indicates the prefix of I indicates the prefix of X of length I, and J indicates the prefix of Y of length J. Okay, so which looks like this, right? So we have X1 up to Xi. Think about them as a list. And then we could have, this is Yj, and this is Y1. So what we end up comparing is this. So we want to compare Xi with Yj. If they are the same, then this could be a symbol in a longest common subsequence. Hence, what we're going to do here now is we are going to find the longest common subsequence of this prefix from X1 to Xi minus 1, and then with the prefix from Y1 to Yj minus 1 and plus 1, because now we just have found a symbol that appears in both strings. And so we got this recurrence relation. When Xi is equal to Yj, and also I is greater than 0, and Y is also greater than 0. Otherwise, if X and I and Yj is not equal, so that means that this cannot be in a longest common subsequence. So what we are going to do is to look at this string X1 to Xi minus 1 with the original string Y1 up to Yj, or X1 up to Xi, and then look at Y1 to Yj minus 1. So we compare this two, and to see which pair of these two pairs contain a longest common subsequence. That means that we're going to use that. Hence, we will look for LCS of I minus 1j and LCS of I j minus 1 and return the longest one. So which means that return the max of it when I is greater than 0 and j is greater than 0 and xi is not equal to yj. Otherwise, when one of I or j is 0, when I or j is 0, then that means that we one of the strings now is one of the strings become empty, and then in this case, the longest common subsequence of that would be 0. Is 0. right? So that will return 0. So that is the recurrence relation. All right, and we can implement this using direct recursion, and the following is the Python code that I call it naive implementation of the above recurrence relation. Okay, so I simply define LCX and take X and Y as input, and then we use I and J to indicate the prefix of X and Y. So it's a direct implementation. So that means that we're going to write. So we check the boundary. If I is equal to 0 or J is equal to 0, return 0, because the LCS of these two strings in this case is 0, because one of the string is empty. Otherwise, then we check if xi minus 1 is equal to yj minus 1. Now, the reason I use I minus 1 rather than I and j is because the index of x and y starts from 0. So we have to take that into consideration. So if they are equal, then we are going to so we remove this, and so add 1 to the length, and then we're going to recursively call LCS on X and Y, but with a smaller prefixes. For X is 1 to I minus 1, for Y is 1 to J minus 1. Otherwise, we compute these two LCS and return the max, the larger one. So that is a straightforward implementation. So next, let's see how long it's going to take. And so here I have two strings, X and Y, and I directly run this function, and that, as you can see here, it takes 23 seconds. Okay, and then LCS is 11. The length of the longest common subsequence is 11. So I'm not going to run it because I don't want to just wait for 20 some seconds running this simple code. So now let's get some better understanding from theoretical point of view and of this naive recursion, how long this naive recursion would take. So we do complexity analysis of it. And so this is simply a direct sort of transformation from the recurrence relation for problems depending on subproblems earlier. And this time we change LCS by time. So we let Tij be the number of steps to compute LCS of I and j. Then we know that T of Ij is equal to T of I minus 1, j minus 1 plus 1 if xi is equal to yj and both I and j are greater than 0. Otherwise, if xi is not equal to yj and both I and j are greater than 0, then the time it will take, we have to compute this, and also we compute this, and then we return the maximum. Okay, so you can simply say, all right, that the running time is at least, so we have to compute this, and then we got to well, take the maximum one. Maybe you would say, okay, take the maximum one is an extra computation, plus 1. So maybe we could simply saying that T of Ij is greater than or equal to this, and for that, we don't even need this need is minus 1. Okay. Because now we have a greater than or equal to. It is actually greater, strictly greater than that. So make it strictly greater. So then we want to find the lower bound in the worst case. So we just need to say, okay, in the extreme case, that the LCS of x and y is 0, namely that for all x and y, xi is not equal to yj, then we're always going to use this form. So this t of m n is strictly greater than t of m comma n minus 1 plus t of m minus 1 comma n. And this is going to be greater than 2 copies of t of m minus 1 comma n minus 1. So we repeat this, and then we run this iteration, and then we can see that when, for instance, when m is equal to n, so it's going to run into 2 to the k times t of n minus k, comma n minus k. When n minus k is equal to 0, we got t00 is equal to 1, and hence k is equal to 1, hence this is exponential type. Tn comma n is greater than 2 to the n in the worst case, when both strings don't have common subsequence, except the empty string, which is always a subsequence of both the empty string. So if they don't have a non-trivial, right, common subsequence, then we get the worst case time. So then using dp, okay, so using dp just means that we're going to use an extra list to remember results, the LCS of prefixes, right? So then and next time if we have to compute this, call the same subproblem, then we don't need to recompute this. This is because that subproblems direct recursion will end up computing the same subproblem over and over again, and dynamic programming ensures that we only need to compute one subproblem once. Okay, so the standard approach is we use an extra space or extra list. We call it memo. All right, so this memo, initially you can think of it as set to 0 or initially set to, let's say, set to -1, and then when they actually have some value greater than or equal to 0, that means that the initial value has been overwritten, and then we simply return that value. So, which means that subproblem for parameters I and j has been computed. So we simply do a table lookup, return the values stored in memory. Otherwise, and if I is equal to 0 or j is equal to 0, we let v be 0. And otherwise, okay, and then we check to see whether xi minus 1 is equal to yj minus 1. If it is, we recursively call man-moist LCS on parameters the prefixes of x and y from 1 to I minus 1 for x and from 1 to j minus 1 for y, and then we pass down memo. And then this time we have found a comment symbol, so we add 1 to the final LCS. Otherwise, we compute this subproblem and with parameters I and j minus 1, and the other one with parameters I minus 1 to j, and return the maximum one. And then all of these will be recorded in V, and then we are going to assign that V to memo of I and j. So now this is a problem has a value, so I'm going to record that. I'm going to store that value there, and then return V. Okay, so this is a straightforward implementation. So now we use the same x and y, then now this time we can run it because it's going to be fast. Okay, so as you can see that it only takes 12 milliseconds and we get the result. Earlier, it takes 23 some seconds. Okay, so that is a big difference. So next time, the next, we're gonna get rid of recursion. So use a bottom-up approach. So to use a bottom-up approach, so it basically just means that we're gonna, in this case, we're gonna have a matrix. Okay, so let's say so the 0 point is here, and then it goes 0, 1 up to m minus 1, and here m is the length of x, and here is 0, 1 up to n minus 1, where n is equal to the length of y. So we're going to fill in the value of this matrix. Okay. So so let's say I is from 0 to m minus 1, and j is from 0 to n minus 1. So when I or j is equal to 0, and we know that it will be 0. So that's what we are doing here. So we call this matrix L. Okay, so this is a setup. And otherwise now, so then for I from 1, so the next one is 1. Okay, so for instance, I want to fill in this. So this time we are going to check to see whether x1 is equal to y1. If it is, and then we will add its so this one, so if it's 1, then we're going to add 1. If it's not, then we are going to see which one is larger. So if it's not, we're going to see the look at whether I'm going to look for the one on top of me. So this is on top, or the one on the left. Okay, to see which one is better. It's greater, and then that will be the value return there. So likewise for any of these things. Okay, so if let's say this is J. Maybe I will put it here, right? So this is J, this is I. So if this one, so because their index is, we use the index, so let's say J minus 1, I minus 1. So if this is the same, and so let's just still use I and J. Okay, so this is I's row, J's column. And then now I want to fill in the value here. So I want to fill I, J. So what we're going to check to see here is that to see whether the corresponding symbols, which is x I minus 1 and yj minus 1, if they are the same, then I know that I'm going to have 1 over here. But then we're going to look for whatever the value in here, and I'm going to add it up. So I will know this value because I build from bottom up. Otherwise, if it's not equal, then we're going to look at the one on top, look at the one on the left, and whichever one is the bigger, we're going to put that value in there. So that is bottom-up approach. All right. So let's we use the same X and Y again. And as you can see, this is quicker, although it's still in the same order, 7 milliseconds versus 12. The reason here is that we don't have recursion overhead. So it is faster. It is faster. And next, we're going to look at complexity analysis of DP approach. So as we said last time, what we really need to look at is the total number of subproblems. And then we're going to look at the relations, recurrence relations, how many subproblems in each, so for each current problem, how many subproblems it depends on. So it depends on 2 of those. And then the total number of different subproblems is m times n. Hence, the running time is not going to be more than 2, right? So we got 2 subproblems and 2 times the total number of subproblems. So 2 times m and 2 times m times m. And obviously with some constant. Okay, so that's big O of m. Yeah. So this is straightforward to analyze. So next, by knowing the length of the longest common subsequence, now we want to construct the actual subsequence. So for that, we need to remember, for instance, in particular, we need to remember in this case, which one we are at. So where we will, from where we come to the current subproblem. So we do need to remember that. So for that, we are going to, again, use the bottom-up approach. Okay, I'm going to call it bottom-up LCS path. So this is the same as before. Now I'm going to use an extra matrix called capital P to remember the past information, the information of the past. So remember where I come from, right? So for the current location I and J, how do I end up here from which is the previous location? So for that, we're going to check. So first of all, again, we're going to, so this is the same. So this L is the same as before. So this part is the same. So what I need to remember is that the where I came from. So if xi minus 1 is greater than is equal to yj minus 1, so which means that I'm from the previous one diagonally. So I'm going to use an arrow to point to my previous location. So in this case, it's up left arrow. Okay. And if this is true, so which means that we compare my left and about the value on my left and also the value above me to see which one is the is greater, then we are going to remember that. So in this case, if the one on top, sorry, the one on top, so I minus 1 means the one on top of me is greater than or equal to the one on my left, then we're going to remember that, yeah, I come from the top. So this is, we point to my previous location and use this up arrow. So this is a unit code for up arrow. So this is a character. Otherwise, it's from the left. So I'm going to point to my left. So this is a left arrow. Okay, so and then we can then print this P, capital P, in a nice way. So we can print this arrow keys because they are just characters. So this two statement is just that I'm going to replace the first row and the first column by the actual strings, right? So the first column should be X except the first element, and then the first row should be Y except the first element. And then we're going to print row by row, right? So we use this statement. Remember this one, it just means that the printing statement below, you are not going to insert a new line, okay? So you're not going to start a new line. So that means that it will be continuous, except the last one. And for the last one, I do want to start a new line. And we're going to use the same X and Y, and then we're going to compute the matrix, and then we're going to print the matrix, right? So this is the matrix we have. All right, so let's compile this. All right, so now we have this nice looking printout. So how do we find the actual longest common subsequence? So we start from here, and then we follow the arrow. So we move. So let's use a different color. Use blue. So we start from here. So it's up arrow, the up arrow. Now the first diagonal, that means that we found the first symbol that is common in both subsequences. So this is going to be A. Okay. And then we follow the arrow. So this is going up left. So we go in here and then up and then left and then find another diagonal. So this is the second symbol that appears in both strings. And then from this up arrow, go in here and then left, left, and up again. So this is A. And then, I'm sorry, this is a diagonal again. So go in there, diagonal again. So this is L. and go up there diagonal again. So this is G. Diagonal again, this is C. And this diagonal, so we're going up here, and then this is going up, and then find another diagonal. So that is A. And then diagonal up left, so go in here, going up there, so find another one. So that's a C, and then go up there because we follow the arrow. So this is left, left, and then find another one. That's A. And this is up here, and find another one. That's T. And going up here, so no circle. Here, find another one, so that's G. And from here, it's auto boundary, so we are done. So the actual longest common subsequence will be GT will be in this direction. Okay, so GTACACGLABA. I'm sorry, this is not B, this is G. This is G, yeah. G, okay, not B, I look at it wrong. So it's with GTACACGLAGA. Okay, so let's run this. This, this. Okay, so that's what we got earlier, GTACACGLAGA. So that is the longest common subsequence. So this is another example, and there is an easier one. Okay, so we run this. So this is the matrix. And again, we go up here. So this is the first one, going up here, up there, and then up. I'm sorry, diagonal, not up. It's diagonal. Going here. Diagonal. Going here, left, diagonal. Going here, left, diagonal, and we are done. So this is going to be B, and this is C, and this is B, and this is A. So BCBA. Okay, so that is the actual common subsequence we found. Okay, so we run the algorithm, and that's what we got. Okay, so this is the end of this video. Thank you for watching.